Can you guys hear me? No? Or now? Is it better? Okay. Yeah. Thank you for coming to the talk. I think the organizers knew that this is going to be me, so they organized just after the coffee break. But thank you for being here. So I'm Kolora. I'm a postdoc at UC Berkeley with Peter Supan, who's over there. We study rockfishes. Rockfishes have this amazing distribution from the coast of Japan to California and Alaska, and towards the south they're distributed to Chile, and they have these really nice longitudinal lines which differs between species. And you have some species of rockfishes, like 4 to 5 species, which are found over the coast of Europe, mainly towards Norway. And as you can see here, this is the sampling distribution or the species distribution of the rockfishes we got from FishBase. And this star over here represents the Baja California region. This is a heat map representing how many species or the species diversity of the rockfishes. And in the Baja California region alone, you can find 30 different species of rockfishes. What makes rockfishes interesting is they have these really nice stratification into genuses, where you have one genus which has more than 100 species, another genus which has 10 species, and all two genuses which have less than 5 species. Oh, sorry. If you look into other fishes, what happens is you have salmonids, which are known to have whole genome duplications. These have a huge number of species or really great adaptive variation. You have cichlids, you have snailfishes, which are not that well studied, and you also have our Sebastes fishes, which are over here. The speciation rates of Sebastes are really high, and they have evolved over the past 6 to 8 million years. The other thing which makes rockfishes interesting is their longevity. They have maximum lifespans which span from 10 years to 200 years, and these are different species over here. And as you can see, the flag or the calico rockfish lives only up to 8 years, and you have the rough-eye rockfish, which is found near Alaska. This lives up to 200 years. Till now, when you look into aging or lifespan patterns or longevity, what they have been doing is compare this across vertebrates or tetrapods, and they try to study the killifish up to the Greenland chart. What happens in these studies is you don't have high resolution in terms of what's happening according to phylogenomics. So you're trying to do a phylogenomic approach of studying rockfishes through their genomes. We are trying to Illumina sequence and create some genome assemblies and study them. But what are the causes of adaptive divergence in chelios in general? You have 4 main causes. One is the ancient polymorphisms, which include genomic rearrangements and duplications, which is common in salmonids. You have insertions of transposable elements near UTRs, which can make or break genes. You have accelerated evolution of regulatory and coding sequences. And you have non-coding RNA evolution, where microRNAs play a huge role in the diversity of species. So we call this the Rockfish Genome Project mainly because we are planning to sequence at least or around 100 species of rockfishes. And currently we have 87 different species sampled, and we have sequenced 61 different species from different regions. And for this talk, I'm just going to talk about 26 different species, which is the first phase of the project. Apart from Illumina sequencing, the plan is we try to Illumina sequence 25 to 30x of coverage for each of the species. We are also planning to build reference genomes up to chromosome level. This is one of the assemblies we generated. We are building the chromosome level of the genome mainly to study structural variation or genomic rearrangements between species, because you have lots of false positives if you just study them through Illumina. Currently we have we are planning to study 7 species, and we have 6 genome assemblies already done, but I'm not going to cover this in the present talk. We also want to study their phylogeny, because there has been some phylogenetic studies saying how these are clustered, but they're mainly dependent on only one mitochondrial marker or 2 nuclear markers. So we want to study this from the genomes. And we want to study the genetic basis of diversity. So initially, the sampling plan was simple. We got samples from our collaborators in Japan towards Alaska, the NOAA helped us. We sampled ourselves at the Baja California region. And we have samples also from Chile, from Juliana. And we have these really nice latitudinal flights where you have one species at different locations. And the really good thing about this species hotspots is if you go into the Baja California region, in one region, you're able to sequence multiple species in a single day of sampling. So this is how they look morphologically. They have really variable life rates too. They have difference in color patterns between populations, between species, morphologies, spines, also their face structure. This one looks a little like puppies. So yeah, they're completely different. And the Baja California region, which I'm especially mentioning over here, this is our favorite spot where close to the Farallon Islands. This is the Golden Gate Bridge in San Francisco. It's about 30 miles. You can just go fishing there, and in one single spot, you can fish up to 15 different species. And our highest count was 9 species till now in a single spot. After doing the genome sequencing, what we tried to do initially was to study their phylogeny. And for this, we generated some Illumina quantic assemblies. And based on the whole genome alignments, we generated the phylogenetic tree. And these are just based on the whole genome alignments. These are not SNPs or coding sequences. And what we found out is that these are really nicely stratified into subclades. As you can see here, these have different lifespans. This ranges from 12 years to 30 years. But you also have these species which have 18 years to 116 years, which is like 5 to 6 times higher compared to one species to another. And there are previous studies which suggest there is ongoing gene flow between them, which we also want to investigate. So one of our main species we want to study is called the roughi. This lives up to 205 years. And we are building the reference or high quality genome for this too. And the way we are building the high quality genome is using Illumina, PacBio, and also HiC data. Initially, since we had the Illumina sequencing, instead of going for a mapping based approach where you call SNPs and stuff, what we did was use the Kmer approach, use the Kmer spectrum in order to see how the heterozygosity looks like. And when you look at the heterozygosity, it's from 0.2% to almost 0.02% to 0.1%. And this is the same across the entire range of chordates, which show 0.01 to 0.15%. So that's what we are dealing with over here. And you can see that the chimps and humans are very like. This chordate study was already done by Molly Prochowski in 2012, and this is one of our references to see what's happening between species. As I told you, the adaptive divergence can also be related to whole genome duplications. So based on the Kmer spectrum of the Illumina sequencing data, we tried to plot the Kmer spectrum, and we didn't see a double peak, which means there can be a whole genome duplication. You saw a smaller peak, you can say there is some heterozygosity going on, but most of these 26 species in the first batch of our study show a single peak. So these are relatively simple to assemble. We don't have genomic duplications. That's what I want to say. And though we don't have genomic duplications, there might be transposable elements or repeat elements which are responsible for making or breaking the genes. So we try to plot from the 26 Illumina quantic assemblies what is the repeat architecture. And we were able to see that less than 10% of the genome is covered by repeats. And when you look at other vertebrates, it's more than 30%, and I think in cichlids it's around 15%. There is no clear stratification by age over here, but the interesting pattern is we have the Sebastolobus, which is the outgroup, which is represented by only 3 species, and they have 20% lesser rito elements compared to the other Sebastis species. This is a common pattern we observed. And apart from this, we did see other kinds of mechanisms like the rito elements, which follow the copy and paste mechanisms. These show differences between the 2 genuses. And there is also twice the amount of line 1 elements in the Sebastes compared to the Sebastopodus. There was one particular species I was pointing out to the tiger and rock, which have 5 to 6 times difference in longevity, and they also show this weird patterns of lineage-specific expansion in repeat elements. So this is one interesting thing here, carrying forward and trying to analyze. Apart from the repeat elements, you can also look at what gene families are expanded or contracted in the rockfishes or fishes in general. And options are really important when you look at divergent evolution in teleos or deep water fishes, because they have huge expansions. But in rockfishes, they don't show any expansions. But the gene family which showed expansion is the transposase family. You can see almost 110 genes which are related to the transposase family compared to sunfishes or cichlids or ancient hagfishes. So we think this might be adaptive divergence, which is mainly related to the repeat expansion than any other mechanisms. So from the initial genome assemblies, we try to look at if there is difference in selection in Sebastes compared to Sebastolobus, which is the species per clade. And what we saw is one of the pathways was overrepresented. This is statistically supported in the Sebastes ancestor compared to Sebastolobus. But since we were looking at longevity patterns too, we tried to compare this in the Sebastes alutianus, which lives up to 205 years. And this also pops up as undergoing gain in selection. So this looks like a problem of looking at signal and noise, and this is what we are currently analyzing. So in summary, what I wanted to show was we have sequenced rockfishes, we have built in phylogeny, we are building their genome assemblies, we are studying their genetic diversity, and we think the repeat expansion is mainly responsible for their adaptive divergence. We are currently investigating the different patterns of accelerated evolution and the presence or absence of microRNAs between different rockfishes. To just give you a gist, what's happening with the genome assemblies is we have contact level assemblies which have N50s of more than 5 MB sometimes, and we have a completeness which is more than 97%, so these are really good qualities. This is the Sebastolobus, which is the species per genome. This has high level of heterozygosity, so we are resequencing this to 150x of pattern correlation. Also, there are patterns of gene flow, so it's not easy to understand their population histories. We are trying to resolve that into subclades and trying to understand what's going on. Yeah, that's all for now. I would mainly like to thank our PI from our lab, Peter Sudman, who's in the audience over here, the captain of our boat, Alexander, who's also a commercial fisherman, Milton Love, the ichthyologist, and lots of collaborators who have submitted samples. I would like to thank you, but before that, we are hiring postdocs and graduate students for computational comparative genomics, not just in rockfishes, but also other vertebrates. If you're interested, you can reach out to me or Peter over here. Thank you all for your time.